All right, good morning. Today we are going to be doing our lesson with learning targets 4 and 6, where we will be finding the probability of independent and dependent events, as well as looking into what conditional probability events are. I'd like for you to notice how many vocabulary words there are for you to record the definitions of in 12.3. Make sure you are recording the definitions. That way, when I'm describing these words and using these words, you actually know what I'm talking about, okay? So example 1, we have 2 coins are tossed, and we need to know the probability that they're both going to be a heads. All right, so your textbook actually deals with this by creating a tree diagram. I'm going to create a use of the space system. So I have 2 spaces because I have 2 coins being tossed. Now, the very first probability, the very first coin, I'm dealing with what is the probability that both are tails? Well, the probability of flipping a coin and getting a tails is 1/2, okay? Because there's only one way to get tails, and there are 2 possibilities. And so one thing you'll always need to recognize with probability is it's always the specific number of occurrences over the total number of occurrences, okay? And then I have another probability of 1/2 for my second coin being flipped because the probability of flipping a tails has not changed. Now, in this scenario, I'm essentially using an and kind of probability where I have the first probability and then the second probability. I flipped one coin and then I flipped another coin. So we're going to multiply these 2 probabilities and we're going to get the probability of both occurrences happening. And 1/2 times 1/2 is going to get me a probability of 1/4. Now, like I said, you should take note of the tree diagram method that your textbook uses because it'll showcase what all the different possibilities are. For example, the first probability that I'm looking at is flipping either a tails or a heads. Now, the tails can either flip next a heads or it can flip next a tails. And same for this head. You can either flip a head or a tails. So notice that there are a total of 1, 2, 3, 4 possibilities, okay? Now, the only one that I actually care about was the chances of me flipping both tails, and this only occurred once. All right, so now we're looking at example 2, where we're actually going to have a probability that's also going to feature combinations from learning target 2. If we read the question, Monifa has a collection of CDs. She has 32 in total. 18 of them are R&B, and 14 of them are rap. As she's leaving for a trip, she wants to randomly choose 6 CDs to take with her. What is the probability that she selects 3 R&B and 3 rap? Few observations, okay? I know I'm dealing with combinations here because no matter what 6 CDs I choose, I'm still going to take them with me. I'm still going to be able to listen to them. So it doesn't matter what order I choose them in, okay? Something to remember, we're going to have the specific number of arrangements over the total number of arrangements, okay? So let's think about the total number of arrangements. In total, I have 32 CDs, and I'm going to choose a total of 6 CDs to take with me. This will be the number of arrangements for that total number of occurrences. Now, in the numerator, I have my specific situation. Now, my specific situation, I have 18 R&B CDs, and I'm going to be choosing 3 of them, okay? One of the key words here that I'm noticing is this word and. And means I have both of these things occurring, which means they are going to affect one another, and therefore I must multiply them, okay? So then, I'm also going to have 14 rap CDs, and I'm going to choose 3 of them, okay? A little word to the wise with how to set these problems up. The n, the total number of things I am choosing from. The numerator's n's should add up to the denominator's n's. Another observation, the r, the number of things I'm choosing. I have 3 and 3, which add up to 6 in the denominator. So like I said before, the specific over the total, the specific number of occurrences, their n's and r's should add up to the denominator, the total number of occurrences, okay? Now, if we were to calculate this, 18 choose 3 times 14 choose 3, it ends up being a very large number. It ends up being 297,024, okay? My denominator, so we have 32 choose 6, and that ends up being 906,192. Now, if we divide the specific by the total, we get approximately 0.32777, or what you can simply say is we have a 33% chance of selecting 3 R&B and 3 rap. Okay. All right, so the next example that we're getting into is the idea of odds. And odds are a little bit different than probabilities, but once you notice the pattern, I promise you they will not be that bad. So let's make sure I point that out. So we have, according to the U.S. National Center for Health Statistics, the chances of a male born in 1990 living to be at least 65 years old of age are about 3 in 4. For females, the chances are about 17 in 20. Okay, a few things that you need to recognize with odds, and I'll make sure my face is still showing so you can see that. 3, for males, that is the specific. Okay, there are 3 males. The 4 represents the total, okay, which the total includes the number of successes and the number of failures. And 3 is also representing the number of successes, which means there's 1 failure. And we're always going to have this ratio of successes to the number of failures. Well, if there were 4 total, the difference between 4 and 3 is a difference of 1, meaning that there was 1 failure that occurred, okay? Now for females, we're going to use the exact same strategy here, okay? 17 represented the number of successes. So we have 17 in ratio to the number of failures. Now 20, that represented the total number of occurrences, including successes and failures. And the difference between 17 and 20 is a difference of 3. So 3 represents the number of failures of the situation. And I should clarify that. Failures means it not occurring, okay? It is the opposite of that success, okay? All right, let's take a look at example 4 now here, and I'll bring my face down so I can also scroll down here. All right, so now we have, suppose 2 dice are rolled. We have a relative frequency histogram, and it shows the distribution of the sum of the numbers rolled, okay? So in this type of example, it's very important that we learn how to interpret graphs, okay? So here we go. Use the graph to determine which outcome is most likely. What is its probability, okay? So the one that occurs most frequently is this sum here, and we see that, I gotta make sure my pen's working. We see that occurring right here when we have a sum of 7, okay? So the sum of 7 occurs most frequently, okay? And the probability of it occurring is according to 1/6, according to our bars here, okay? Now it says use the table to find the probability of having a sum of 9. And notice that I just interpreted what this notation meant. P of the quantity S equals 9. That means the probability of the sum being 9. Now according to the table, here's where we get a sum of 9. And the bar shows me that that occurs 1/9. That is my chances, 1/9. Now it also says what other sum has the same probability, and that also occurs when I have a sum of 5, okay? They have the same chances. Lastly, it says what are the odds of rolling a sum of 7? Now notice that 1/6 was not the odds, okay? Let me write that out, not the odds, okay? And recognize the fact that we have a ratio of the number of successes to the number of failures, okay? So in this scenario here, the number of successes that occur is 1, okay? So we're going to have a ratio of 1 to the number of failures. Now this is where we look at our total. The total 6 represents the number of successes as well as the number of failures. So the difference between 1 and 6 is a difference of 5. So the ratio, or the odds, is a 1-to-5 odds of rolling a sum of 7. All right, so we're now taking a look at 12.4, where we're be finding the probability of 2 independent and 2 dependent events, okay? So the very first one that we're going to take a look at is example 1, and let me scroll down a little bit here. At a picnic, Julio reaches into an ice-filled cooler containing 8 regular soft drinks and 5 diet soft drinks. He removes a can. Then he decides he's really not that thirsty, so he puts it back, okay? What is the probability that Julio and the next person to reach into the cooler both randomly select a regular soft drink, okay? So I'm really looking here at 2 probabilities, or 2 events, okay? The first event is when Julio draws a can, okay? So the probability that I draw a regular soft drink, we have specific over total. So there are a total of 8 regular soft drinks. Out of my total number of drinks in total is 8 plus 5. That's going to be 13, okay? My next probability, I'm going to be multiplying these because it's one then the other, one and then the next draw, okay? The probability has not been affected, and the reason it has not been affected is because Julio put his drink back, which meant that the total number of drinks has not changed, and the total number of regular soft drinks has not changed. So once again, then, our total for soft drinks that are regular is 8, and our total number of drinks in general is 13. So we have 8/13 times 8/13. So our total probability here is going to be 64 out of 169, and that's going to be approximately 0.38, so 38%, okay? Our next example here, we have 3 independent events occurring. So we have a board game, and we have 3 dice being rolled to determine the number of moves for the players. What's the probability that the first die shows a 6, the second die shows a 6, and then the third die does not, okay? So there are 3 events occurring, so I'm giving myself 3 placeholders just so that I mentally know that there are 3 more things happening. Now the first probability, the first die shows us 6. Well, there's only one way to roll a 6, so the specific occurrence is 1 out of the total number of ways I can roll a dice, which is 6, okay? Once again, the second die shows a 6. So once again, only one way to roll a 6 out of the 6 different ways to roll a dice, okay? Now the last event, the third one, does not. What this is actually called is a complement, the opposite, okay? Complement is a vocabulary word that you actually do need to know, so I'm going to write that down right here. Please make sure you are recording the complement. The complement is the opposite of an event, so it not showing a 6. So the reverse probability of 1/6 would be 5/6, okay? So the total number of probabilities between the event and its complement should in total produce 100%. 1/6 and 5/6, that's going to add up to be 100%, okay? But back to the problem that we're dealing with here. What's the probability of these events all occurring? Because we want all 3 events to occur, we're going to multiply all their probabilities, okay? And we are going to get a probability of 5 out of 216. So you actually don't have great odds of having this occur. And I think if you really think about it logically here, the reason that is happening is because you are so limited in these first 2 dies of what you want to roll. All right, so now we're into 2 examples that are going to deal with dependent events. So I'll talk about why they actually will be dependent events and what the key words are in the examples. So we have a game show host who's drawing chips from a bag. There are 10 total chips in the bag. 6 of them show a television prize, 3 of them have a vacation, and 1 of them has a car. And the host is drawing chips at random and does not replace them, okay? Find each probability. Well, the word does not replace them means that because I'm taking these chips out of a bag, the total number of chips has changed, which will affect the next draw, okay? So first off, we have a probability of drawing a vacation, then a car. And notice that it's very important that we recognize that the order here will affect the way we solve this problem. So the very first probability, what is the probability that I draw a vacation? Well, there are 3 chips for vacation, and there are 10 total chips, okay? My next probability, so we have 1 of those chips out, okay? So now we need to recognize that our total number of chips has changed to 9. Now the car, there is still 1 car chip, okay? So that has not been affected. So we have 3/10 times 1/9, and that's going to get me 3/90, which actually will then simplify to 1/30, okay? So slim chances here. Next probability, we have 2 televisions. So we have first draw being a television and the second draw being a television. So in the first probability, there are a total of 6 television chips out of 10 total chips. Now the next probability, what we are going to do is we are under the assumption that that first draw did actually take out a television chip. So So now there are no longer 6 television chips, there are 5. And now that we've taken a chip out and we did not replace it, there's a total of 9 chips, okay? So when we multiply these out, we have 6/10 multiplied by 5/9. That's going to simplify to actually being a probability of 1/3. So you have a 33% chance of drawing 2 televisions. So that's actually pretty good odds here. So example 4, where we have 3 dependent events. 3 cards are drawn from a standard deck of cards, okay? Side note, important information. There are 52 cards in a deck of cards. If you do not know your information about decks of cards, please make sure you're making a little mental note, and maybe in the space provided here, record some facts about decks of cards, anything that I say that might be helpful. So they're drawn, and it's without replacement, aka every time I draw a card, it's going to affect the total number that I have. Find the probability of drawing a diamond, a club, and then another diamond in that order. So there are 3 events that occur, okay? The first event is me drawing a diamond, okay? Well, diamond is one of the 4 suits in a deck of cards, and there are going to be a total of 13 diamonds in that deck of cards out of the 52 cards that exist, okay? So then the next probability that I'm dealing with is drawing a club, okay? There's my pretty atrocious drawing of a club, okay? A few things to notice. It's without replacement. So now that I had my first draw, I have 1 less card in that deck of cards, bringing my total down to 51. Now, because I'm under the assumption that the first one drew a diamond, there are still going to be 13 clubs because club is one of the 4 suits of a deck of cards, okay? Now, the last probability, we have now drawn 2 cards, so therefore the total number of cards is down to 50. And because this last one is going to be another diamond, I need to remember that the first event that I had was drawing a diamond. And because I'm assuming that I did draw that diamond, the total number of diamonds has dropped down to 12, okay? So what we're going to do is we're going to multiply these 3 probabilities, and we get a total of 13 out of 850. So really slim chances here. It's actually 0.015, or about 1.5% probability that this will occur.